Lesson number one, if it seems like the answer is not obvious here, it's because these problems aren't obvious. You got to stop and think and experiment a little bit. So give me a second here to think about this. Okay, well actually we don't have to think too long here. So we should always try to number. We should always try to number. Of course, if it's too hard, we'll give up. But we should ask if there was any landmarks put in here to help us.
18.
Yeah, this is a big landmark here for us. So let's call this the number 1 carbon. The number 1 carbon is attached to the oxygen. So this is oxygen isotope 18. So we can do that. This just means an isotope of oxygen, right, with a different weight than usual. It just means that it's labeled for us.
Oh, you label the carbon opposed to labeling the oxygen?
Right. In a sense, the oxygen's already labeled. It's got the number 18,
okay.
right? But remember that the 18 just means that this is an unusual isotope of oxygen. The key thing is this is a different isotope than these oxygens. Right. So we know that this oxygen must be the same as this one over here. They both got the 18s. So this is our landmark. Okay. Anything else? Well, call this number 2. I guess it's reasonable to think that this is number 2, connected to the OH. We call this number 3. I guess it's reasonable to call this number 3 because this is also connected to an OH. Okay, maybe that's enough numbering for the time being.
And couldn't 2 be in the ring?
Oh, well.
You know, 2 and 3 could be. Oh,
yeah,
right.
This is
the same
symmetrical.
anyways. Yeah.
So it doesn't matter whether you call this 2 or this 2.
Right.
All right. So do those numbers make sense?
Mm-hmm.
Yeah. Okay. Maybe now's a good time to put off the numbers. All right. So any opinions about what would happen first in this mechanism? Do we know anything about what's going to be the first step?
We take an alpha hydrogen, and I assume we take it from the left molecule over the right, just because there's almost 2 possibilities on the left where to take it from, and on the right.
Okay, so let's talk about that. So it's good that you saw we have a strong base. Anytime we have a strong base, we should be thinking about deprotonating alpha carbons in this part of the course. This guy.
Sorry, very quick. You know how we had in the other problem where we weren't doing carbonyl chemistry, we had like an ONE minus or something strong that attacked the carbonyl. How do we know if we're attacking the carbonyl or if we're taking an alpha hydrogen?
Yeah, that's a problem. So basically the problem is that oxygens with full negative charges are both good nucleophiles and good bases. Oxygens with a full negative charge are both a good nucleophile and a good base. So how do you know what to do? Well, first of all, from this point on, if you have a chance to deprotonate an alpha carbon, you should, pretty much. I don't know if this will work 100% of the time, but pretty close. From this point on in the course, if you have a chance to deprotonate an alpha carbon, that's going to happen first. And do you remember what's the instructor's slogan for that? He loves to say acid-base reactions are fast, right? Acid-base reactions are fast. So if you have a chance for this to act like a base, that's going to happen before it can act like a nucleophile. So if there's a chance for this to act like a base and take off a proton, that's what it's going to do, generally speaking. That's basically the answer to that.
And you're taking alpha proton opposed to a proton off of the OH?
Oh, well, that's a good question.
I saw that happen.
It can actually do it either way. It could do it either way. So how are we going to decide what's going to happen here? Now, first of all, remember, we're not trying to figure out what's going to happen the most often. Because remember, this is a mechanism problem. He's not saying this is the major product. He's just saying it's a product. So how do we know what we should do? We should do whatever it takes to get this product. That's the answer for mechanism problems. For mechanism problems, you shouldn't do what kind of seems most likely. You should do anything that seems reasonable that will help you to get to the product that you're going to. Okay, so you're right that this is a base, and certainly it's not going to act like a nucleophile because acid-base reactions are fast, and there's plenty of things that this could deprotonate. So, but the hard part is, who the heck is it going to deprotonate? So we'll have to take our time and figure out who is going to deprotonate. And here's how we're going to figure that out. Here's where the numbering comes in. We decided that this was the number 3 carbon, right? But what's the difference between the number 3 carbon in the starting materials and the number 3 carbon in the products?
Now it's connected to more things.
To another what? What's the atom that this is attached to here? Another, what's the extra atom that the number 3 has in the products that it didn't have in the starting materials? Another carbon. We want to be as specific as possible. We want to be as specific as possible about what change occurred between the starting material and the product, because then we can ask how can we make that change. You always want to be on the lookout for new carbon-carbon bonds. There's not that many ways to make carbon-carbon bonds. So if you see a new carbon-carbon bond, you want to focus on that. It looks like this number 3 here has made a new bond to a carbon, because after all, over here, this was a primary, and over here it's a secondary. Okay, so we know this is going to, so we want this guy to attack a carbon, so it looks like this is the guy we're going to deprotonate.
Okay.
That's how we figure out who to deprotonate. Now we're not saying that this is the only guy who can deprotonate, but we want, in order to get this product, we have to deprotonate the number 3. Does that make sense? Yep. Okay. And again, the key lesson here is how impossible this would be if we hadn't got the numbers in the first place and started comparing the two pictures. That's really the only way to do this type of problem. So we're going to deprotonate this number 3 carbon. And then we, of course, the base would be deprotonating it. I guess I won't go through all the mechanisms here. So then what? Any ideas what would happen next?
I mean, we know we want to integrate the two, so that could attack the carbonyl-carbon.
Yeah. Is that a reasonable reaction that we've seen in the past? Enolates attacking a carbonyl-carbon? Absolutely.
Except the thing is that it makes a ketone, right? That's the final product. So don't we want to actually use an oxygen to do the attacking if we're forming a ketone?
Well, this is the product, right? I'm not quite sure why you said there was a ketone. There are no ketones in here.
It's an O. We've put an O in the ring. Sorry.
Oh, that's right. You're putting an O in the ring. Okay.
So don't you want to use an O to do some form of attacking?
Yeah. So you're right. You're right. Let's just press forward with this idea, and then I think your concern will clarify as we go along. But you're actually on the right track there. But for the time being, we know that what's going to happen is that this number 3 over here has to form a carbon-carbon bond. Okay. Basically, the thing is there's more than one thing that's going to happen here. So we can take care of that issue that you're talking about as we go on. But you're right. That's something else that has to happen. But for the time being, now that we have this negative charge here, we know this has to act like a nucleophile, and it would make sense for it to attack this. That's a reasonable reaction, and that would also give us what we want. So now let's call this the number 4, and then that would make this the number 4 in the product. Remember to keep trying to number both pictures as much as you can. And now this looks good because the number 4 should have an oxygen like it does over here. So have this come in and kick that off like that. All right, so let's draw what that would give us as a product.
Wait, how did it make a ring all of a sudden?
I'm sorry, it hasn't yet. I'm just doing this as a thought process.
Okay.
So one thing that's challenging here is that the products get pretty complicated. So as usual, I like to use the redraw and modify technique. But this is going to be a little different. I'm going to redraw the final product and modify it. So this is ultimately what the final product is going to be. Now, which of these bonds have we not yet formed? Well, let's see here. So we should have, I have to put my numbers in. So this is 1, 3, and 4. So we just had our number 3 carbon attack the number 4. But that would have put a negative charge on this oxygen. We can call this 5 and 6 now. So this would be 5 and this would be 6. Now we can go ahead and number everything. At this point we can number everybody. So as soon as possible you want to number everybody. Now in the final product, the number 5, so I can put those numbers in here too, number 5 and 6. Now the number 5 has the OH here, that's good. The number 6, now in the final product the number 6 just has an O, but at this point it should have a OH. So I'll erase this bond. And this was our number 1 over there. So we have the number 5 and the number 6. All right, so this is our next intermediate. This is the intermediate we'll get when the number 3 attacks the number 4. The key thing is notice how I'm trying to draw the intermediate so it looks as much like the final product as possible. This is another very useful step. Try to draw the intermediate so it looks as much like the final product as possible. That makes it much clearer what's going to happen next. I got to admit that what I just did here is not that easy. What I did was I took the final product and I erased the things that hadn't happened yet.
Yeah.
That works for me, but that's kind of difficult. So you have to find some way to get the right product here, and then maybe redraw it so it looks more like this product over here. But would you agree that this is the right intermediate now?
Yeah.
Yeah?
I don't know, I can't do what you just did.
Okay.
It's not gonna work.
Well, basically, we know that the number 3 should now be bonded to the number 4. So we have this
so
bond.
could you show it as just like doing it, like,
Well,
just 3 to 4?
plus look, number 1 has a double bond O for now.
Oh, so I didn't get it right either, did I? So the number 1, yes. So this is also a change I should have made. So maybe this method is too hard for me too. So that would put number 18 over here. Okay, that's right. All right, maybe that's not the best method I ever came up with. So that gives us this. So all right, so you were right to look quizzical a second before.